roaring engines and the constant push for speed, there is a moment of silent, absolute necessity. The moment you need to stop. That critical transition from unchecked momentum to controlled safety hinges on a component that works in the shadows, enduring immense forces, transforming violent kinetic energy into dissipating heat thousands of times over its life. This is the story of the unsung hero of motorcycle performance and safety. The brake disc. Today, we venture inside the high-tech heart of modern manufacturing to unravel the precise, step-by-step journey of how a motorcycle brake disc is made, from a pile of raw, earthy materials to a gleaming, life-saving piece of engineered perfection. Our story begins not on the factory floor, but in the science of metallurgy. The soul of a brake disc is its material. For the vast majority of motorcycles, from daily commuters to apex hunting sport bikes, that material is a special high-carbon alloy of cast iron, often a grade known as G3000, or a high-silicon molybdenum iron. This is no ordinary iron, it is a carefully formulated recipe, a secret blend for many manufacturers, chosen for a sacred trio of properties: excellent thermal conductivity to carry heat away from the pad contact zone, inherent wear resistance for longevity, and most crucially, a high and consistent coefficient of friction to provide that predictable, firm bite every time the lever is pulled. The raw ingredients, piles of recycled steel scrap, primary pig iron, and precise alloys like ferrosilicon and ferromolybdenum, are gathered. Computer-controlled scales measure each component down to the gram, because consistency here is the foundation of safety. A single percentage point's deviation in carbon or silicon can alter the disc's very character under the extreme stress of braking. This meticulously weighed charge is then fed into the mouth of a roaring furnace. Within, temperatures skyrocket past 1,500 degrees Celsius, over 2,700 degrees Fahrenheit, reducing the solid metal into a bubbling, glowing crucible of liquid potential. This is a vat of pure molten transformation. Before the pour, a sample is taken, cooled, and analyzed by a spectrograph. This machine reads the elemental signature of the metal, confirming the chemistry is perfect, ensuring batch after batch will perform identically. While the metal reaches its liquid state, its future shape is being prepared in another part of the foundry. Here, automated molding machines create the disc's negative image from resin-bonded sand. The molds are formed in two halves, known as the cope and drag. The cavity inside is simple but definitive. It will form the disc as blank, the rough as-cast shape that holds the promise of the final product. The moment of truth arrives with a stream of incandescent orange metal. The furnace tilts, and the molten iron flows like luminous honey into the waiting sprue of the sand mold, filling every contour. As it solidifies, a key microscopic event occurs. The carbon within the iron forms into graphite flakes. This unique structure, inherent to gray iron, is what grants the material its excellent damping characteristics, its ability to absorb vibration, and its relative ease of machining later on. The filled molds travel down a cooling line, the fierce glow within them fading slowly from yellow to cherry red, and finally to a dull black over several hours. Once cool, they reach a shaking station. The molds vibrate violently, and the sand shell fractures and falls away, revealing the newborn brake disc castings within. They emerge as dark, rough objects, covered in a fine scale of oxidation, with lumps of excess metal. The gates and risers that fed the molten flow still attached. They bear only a faint primordial resemblance to the finished part. This is where the art of subtraction begins, where precision engineering sculpts the rough form into a geometrically perfect component. The castings, now called blanks, are transported to a clean, well-lit machining hall. The first stop is almost always a CNC lathe. A worker clamps a rough blank onto the lathe's chuck. With a command, the machine whirs to life. The blank begins to spin, and a sharp carbide cutting tool approaches. On contact, a tight continuous spiral of dark iron swarf peels away, and beneath it is revealed a smooth, shiny silver surface. This is the first act of creation through removal. The lathe's primary mission is to establish the disc's critical reference surfaces. It machines the mounting face, the precise surface that will bolt directly to the motorcycle's wheel hub, to an exacting flatness, often within a few hundredths of a millimeter. It also turns the outer diameter and begins to skim the two faces that will become the braking surfaces. This initial machining ensures the disc will run true, without axial or radial runout, wobble, when finally installed. From the lathe, the disc often travels to a multi-axis machining center. Here, the transformation becomes more intricate. Drill bits whirl to life, cutting the exact pattern of mounting bolt holes with robotic precision. End mills trace paths, machining the internal splines or the carrier screw holes, and carving any aesthetic contours or lightening pockets into the inner bell section of the disc. For high-performance floating discs, this stage is where the separate aluminum center carrier or hat is also machined, and the precise slots for the floating buttons or bobbins are cut. Now, we create the disc's signature, its functional fingerprint. Before any holes are added, many discs receive a pattern of shallow curved grooves machined into the friction surface. These are often called scrub lines or conditioning grooves. They are not merely decorative. Their purpose is to gently scuff the surface of new brake pads during the critical bedding-in process, optimizing contact and heat transfer from the very first stop. They also serve as microscopic channels to clear away water, fine debris, and combat pad glazing. For performance and premium street applications, the next step defines the disc's appearance and advanced functionality, drilling and slotting. A plain machined disc is mounted onto a massive CNC-controlled drill press. Above it, a solid carbide drill bit, engineered for the task, rotates at high speed. In a shower of sparks and a sharp metallic whine, it plunges through the iron, emerging cleanly on the other side to create a perfect round hole. This process is repeated hundreds of times in a precise pattern across the entire friction ring. This is cross-drilling. The reasons are deeply engineered. First, heat dissipation. The holes massively increase the surface area of the disc, acting like tiny radiators to pull heat out of the mass and radiate it away into the passing air. Second, weight reduction. Removing this material lightens the unsprung weight and the rotating mass, improving suspension response and acceleration. Third, and vitally, they provide an escape route for gases. Under extreme heat, brake pads can release gases. If trapped between the pad and disc, these gases can create a lubricating layer, leading to a sudden loss of braking power known as gas fade. The holes vent these gases away, maintaining consistent pedal or lever feel. Alongside, or sometimes in place of holes, come slots. Using a thin grinding wheel or slitting saw, radial channels are cut from near the disc's inner radius out towards its edge. These slots perform a similar duty, but are particularly aggressive at scrubbing the pad surface clean, constantly wiping away glazing and maintaining a high-friction interface. They also play a strategic role in heat management by providing controlled paths for thermal expansion, helping to prevent the random, dangerous stress cracks that can form in a solid, overheated disc. Think of a disc under the immense thermal load of a racetrack or a long mountain descent. A solid disc can develop concentrated hotspots, leading to uneven pad transfer, warping, and fading performance. A drilled and slotted disc, by its very design, distributes that heat more evenly across its entire area. The holes and slots break up the heat patterns, preventing localized thermal crises and maintaining consistent, predictable stopping power. After the aggressive machining operations, the disc requires refinement and strengthening. It enters a shot-blasting cabinet. Inside, it is bombarded by millions of small, hard steel beads propelled at high pressure. The cacophonous ringing is the sound of transformation. This process does more than clean off residual scale. It hardens the very surface of the metal, improving its wear resistance, and it creates a uniform, matte gray surface texture that is ideal for the next step. Most critically, it acts as a final inspection, as any hidden casting flaw or subsurface weakness will often be revealed by the blasting process. For many performance-oriented discs, the next step is a journey through a furnace for heat treatment. This is not to harden the iron like steel, but to anneal it, to stress relieve it. The discs are slowly heated to a specific temperature in a controlled atmosphere, held there to allow the internal atomic structure to relax, and then cooled at a prescribed rate. This meticulous thermal cycle releases the internal stresses locked into the metal from the violent cooling of casting and the pressures of machining. The result is a disc that is dimensionally stable, far less prone to warping under the wild thermal cycles of hard use, and one with a more uniform internal grain structure for ultimate durability and consistency. With its form finalized and its structure stabilized, the disc must now achieve perfect harmony. Every single brake disc undergoes dynamic balancing. Placed on a machine similar to a wheel balancer, the disc is spun at a high speed. Sensitive sensors detect the slightest imbalance, a heavy spot that would cause a minute but intolerable vibration at the wheel. A monitor displays a spike on a graph pinpointing the location of the excess mass. The solution is elegant and minimal. On the inner bell section, well away from any critical stress areas or friction surfaces, a small precision drill takes a shallow divot out of the metal, removing just a few grams of material. The disc is spun again. The graph now shows a smooth line. The imbalance is corrected. This ensures that at highway speeds, the rider feels only smooth rotation, not a dangerous handlebar-shaking tremor. The final stage is about protection and preservation. To defend against its eternal enemy, corrosion, the disc receives a protective coating. The discs, hanging from an overhead conveyor, descend into a bath of a special chemical solution, often a black oxide or zinc phosphate process. This is not a paint that sits on top. It is a conversion coating. The chemicals react with the iron itself, creating a new molecularly bonded layer of magnetite on the surface. The disc emerges with a deep, consistent, matte black finish. This coating is tough and corrosion-resistant, protecting the intricate drilled holes and the inner bell from rust, especially from road salts and weather. Every disc is also given a final, meticulous visual inspection by trained human eyes, looking for any imperfection in the machining, coating, or structure. Only the discs that pass every single test without compromise are allowed to proceed. These packages are stacked on pallets, ready for shipment to the assembly lines of major motorcycle manufacturers or to the warehouses of aftermarket performance parts distributors. So the next time you ride and you gently squeeze that brake lever, feeling the motorcycle slow with obedient, confident authority, it is a masterpiece of applied physics, materials science, and manufacturing rigor, all dedicated to one simple, vital purpose. Have you ever stopped to think about the one part of your car that literally touches the ground? Not the engine, not the fancy suspension, the humble tire. It's the only thing standing between your 2-ton machine and the road beneath it. And yet, most of us never give it a second thought. We obsess over horsepower 0 to 60 times and paint colors, but without those round rubber rings, you're basically sitting in a very expensive paperweight. Tires are often called the soul of movement, and that's not just a poetic phrase tossed around by car enthusiasts. These circular rings of rubber are the silent force behind almost every aspect of driving. They're the reason a Formula One car can carve through a high-speed corner like it's breaking the laws of physics, why a heavy family SUV can stop safely on a rain-soaked highway, and why that long summer road trip doesn't end with you fishtailing into a ditch. Every time you press the accelerator, crank the wheel, or slam the brakes, it's the tires translating all that mechanical power into motion. They dictate how quickly you launch off the line, how confidently you handle a sharp curve, how short your stopping distance is, and even how efficiently your car sips fuel. In short, they're doing far more heavy lifting than most drivers ever give them credit for, quietly shaping every second of your journey from the moment you start the engine. But here's the part that'll blow your mind. Despite being so crucial, a tire starts its life as something that looks nothing like a tire at all. It's not black, it's not round, And it certainly isn't tough. It all begins as a sticky, milky white sap dripping out of a tree thousands of miles away from where you're driving right now. Deep in lush tropical plantations, skilled workers move with almost surgical precision, using sharp practiced cuts to tap rubber trees and release their milky white latex, a natural liquid rubber that's been used for centuries. This sap might look fragile and harmless, but it's the starting point of one of the toughest materials on Earth. Drop by drop, it drips into small cups strapped to the tree, collected over hours in a process that's as much art as science. But on its own, this raw latex is far too soft, too elastic, and nowhere near strong enough to survive the intense heat, pressure, and punishment that tires endure. To make it usable, workers immediately mix it with ammonia to prevent it from spoiling, then concentrate it to boost its strength and stability. The liquid is rolled into thin, flexible sheets, the first real building blocks of a tire, and carefully dried before being shipped off to giant industrial plants where its transformation from tree sap to high-performance engineering marvel truly begins. Now here's where science takes over. Natural rubber is strong, but modern tires demand more durability, more resistance to heat, and more flexibility in freezing cold. That's why it's blended with synthetic rubber, a man-made material created from oil and gas through a process called polymerization. By linking molecules like butadiene and styrene into long chains, engineers build a super strong material that can handle thousands of miles of punishment without breaking a sweat. In fact, more than 60% of a modern tire is synthetic rubber. And if you thought rubber was naturally black, think again. It's actually off-white until manufacturers mix in carbon black, a fine powder that massively boosts strength and wear resistance. They also throw in softening oils to keep the rubber flexible, sulfur to improve bonding, and dozens of other chemical additives that tweak properties like hardness, temperature resistance, and curing speed. More than 30 ingredients are carefully measured and blended in industrial mixers that reach scorching temperatures and massive pressures. After a few minutes, the once white sap is now a thick jet black compound, the backbone of every tire. This compound is then rolled into large sheets and cooled, but we're still miles away from anything resembling the final product. At this stage, the material is strong, but it's just one part of a complex, multi-layered puzzle. The next step is reinforcement, and this is where tire making stops looking like mixing ingredients in a kitchen and starts looking like high-precision engineering. Those thick black rubber sheets that started life as tree sap are now flattened, stretched, and layered with ultra-strong synthetic fabrics, each one carefully coated with rubber and bonded together under intense pressure and heat. You can think of these layers as the skeleton or bones of the tire. They're what give it shape, strength, and the ability to flex without failing. But that's only half the story. Next come the steel belts, hair-thin, high-tensile wires that are meticulously aligned and woven into the structure before being sealed inside the rubber. These belts are like the tire's hidden armor. They help it keep its form at blistering highway speeds, they absorb and distribute impact forces to resist punctures, and they provide the rigidity needed to handle the massive loads that cars, trucks, and even airplanes put on them every single day. Without these reinforcements, a tire would wobble, deform, and wear out in no time. With them, it becomes a precise, load-bearing machine, strong enough to handle thousands of pounds while still flexible enough to grip the road through every twist, turn, and sudden stop. By now, we've got the materials, but they still need to become a tire. That's where the building phase begins. In giant automated assembly lines, robotic arms carefully layer each piece, inner liners, sidewalls, fabric plies, and steel belts onto a large rotating drum. Every layer must be perfectly aligned, pressed, and tensioned. We're talking tolerances within 1/10 of a millimeter. Cameras and sensors monitor every move, while computers make micro adjustments in real time to ensure nothing is out of place. A single mistake here, even a tiny air bubble or misaligned strip, could mean the difference between a safe tire and a catastrophic blowout. Once the raw tire carcass is assembled, it's still soft and shapeless, like a rubber balloon waiting to be inflated. Compressed air is pumped inside to give it its round form, and the structure begins to resemble the familiar donut shape we all know. but it's still missing one crucial feature: the tread. The tread is where rubber meets road, literally. It's the part that grips asphalt, channels water, and provides traction. In smaller factories, the tread might be attached separately at this stage, pressed onto the soft tire shell before curing. But in larger, high-tech plants, the tread is formed during a process called vulcanization, and this is where the magic happens. The unfinished tire is placed inside a two-piece metal mold that's engraved with the exact tread pattern. The mold clamps shut like a giant waffle iron, and then things heat up. Literally, steam or superheated fluid is pumped into a flexible bladder inside the tire, forcing the soft rubber outward until it presses tightly into every groove of the mold. At the same time, the mold is heated to around 160 to 180 degrees Celsius, 320 to 356 degrees Fahrenheit. This heat triggers a chemical reaction between sulfur and the rubber molecules, locking them into a strong elastic network. What was once soft and pliable is now tough, resilient, and ready to handle the road. This process doesn't just give the tire its final shape, it's what gives it its soul. Vulcanization determines how well it grips the road, how much heat it can handle, how long it will last, and how it behaves in extreme conditions. It's the moment when everything, a sense of design, engineering, and chemistry, comes together. But the story of a tire doesn't stop once it leaves the factory or even after it's recycled. In fact, its real journey begins the moment it meets the road, and that's where the hidden science behind those 4 black rings really comes to life. Think about it for a second. Every time you accelerate, brake, or take a sharp turn, those tires are translating mechanical power into motion. They're absorbing impacts, dispersing heat, maintaining grip on dry asphalt and wet roads alike, all while carrying thousands of pounds of weight at highway speeds. And they do this silently, invisibly, without asking for credit. That's why engineers often call tires the translators of a car. Your suspension, engine, and brakes can be cutting edge, but none of it matters if the tires can't deliver that performance to the ground. One of the most fascinating parts of a tire's life is how it changes with use. From the very first mile, its rubber compounds begin to cure even further due to heat cycles. Its tread gradually adapts to your driving style, almost like a custom-fitted shoe. Even the microscopic texture of the tread evolves, developing tiny abrasions and channels that affect how water is dispersed during rain. This constant evolution is why fresh tires feel slightly different after a few hundred miles. They're literally breaking themselves in for peak performance. But this constant contact with the road is also why maintenance matters so much. A tire's performance isn't just about its design, it's about how you care for it. Underinflated tires, for example, flex more than they should, generating excess heat and wearing out faster. Overinflated ones lose contact with the road, reducing grip and increasing stopping distances. Even something as simple as rotating your tires every 5,000 to 8,000 kilometers can make a huge difference. It evens out wear, extends their lifespan, and ensures your car handles consistently no matter the conditions. And let's talk about tread, the part of the tire that directly interacts with the road. Most people only notice it when it's almost gone, but it's arguably the most important safety feature on your entire vehicle. Deep, healthy tread channels water away, reducing the risk of hydroplaning. It provides the biting edges that keep you steady in snow or mud. And on performance cars, the tread pattern is finely tuned to balance cornering grip with straight line stability. Once that tread wears below about 2 millimeters though, its ability to do all that drops dramatically, and so does your safety margin. What's even more incredible is how specialized tires have become. Decades ago, one type of tire had to do everything. Today, there's a tire for every possible scenario. Summer tires use softer rubber for maximum grip on hot pavement. Winter tires stay flexible in freezing conditions and bite into snow and ice. All-terrain tires sacrifice a bit of comfort for the rugged durability needed off-road. And then there's the extreme stuff, like Formula One slicks that heat up to over 100 degrees Celsius in minutes, or run flat tires that can limp you home even after a puncture. Each one is a masterpiece of engineering, tailored for a specific job. And yet, no matter how advanced the technology becomes, the fundamental principle stays the same. That small patch of rubber, often no larger than the size of your hand, is the only thing keeping your entire vehicle connected to the world beneath it. That's why engineers say tires aren't components, they're lifelines. They're the difference between a controlled stop and a crash, between gripping a corner and skidding off the road. The future of tires is evolving too. Manufacturers are experimenting with airless designs that never go flat, smart tires with embedded sensors that monitor pressure and temperature in real time, and even eco-friendly compounds made from dandelions and recycled plastics. Imagine a future where your car warns you that your tread is wearing unevenly, or where the tire itself adjusts its pressure automatically for maximum efficiency. These aren't science fiction ideas, they're already in development, so the next time you get behind the wheel, think about everything happening beneath you, the chemistry, the physics, the decades of innovation, all condensed into that simple ring of rubber. It's more than just a circle spinning on asphalt. It's the foundation of every journey, the silent partner that turns horsepower into forward motion, and the single most important safety feature your car has. If this deep dive into the secret life of tires gave you a new appreciation for the cables that charge phones, sync data, and keep devices running, they seem simple. But behind every strong, flexible USB cable is a fascinating process where ultra-fine copper, molten plastic, weaving machines, and precision tools come together in perfect sync. Right from the raw copper wires to the final bend test that breaks them, there's a whole world hiding inside every wire. It all begins with copper. Not just one strand, but 50 razor-thin copper threads that come together to form a single strong conductor. They're twisted or stranded into one bundle. It's not just about strength, though that matters, it's about flexibility. A single thick wire would snap with repeated bending. But twist 50 tiny threads, and you get the strength of a rope with the bendiness of a vine. This stranding process is a dance of precision, where every copper strand must flow in perfect alignment. And the machine that handles this, it doesn't pause, doesn't blink, just feeds the wires in, spins them with rhythmic consistency, and sends out perfectly stranded cores. Now, stranded wires alone aren't enough. These tiny conductors have to be shielded from the chaos of the world, electromagnetic interference, temperature shifts, friction. That's where shielding steps in. A wrap of aluminum foil comes around the stranded core, turning the cable into a mini fortress. This isn't ordinary foil either. It's ultra-thin, lightweight, but incredibly effective at bouncing off stray signals. Wi-Fi routers, Bluetooth devices, electrical noise, all of it blocked out. This shield ensures that when data flows, it flows clean and fast. Inside a typical USB cable, there are usually 4 internal wires, each one insulated, color-coded, and ready to transmit power and data. But before they can be bundled into the final cable, something clever happens. Talcum powder, yeah, baby powder, is dusted between these wires. Why? Because when the plastic sheath is extruded around them, they shouldn't stick together. Talcum keeps everything smooth, letting the wires move slightly within the sheath without damaging each other over time. This tiny step makes a massive difference. Without talcum, the plastic sheath could cling to the wires too tightly, causing stress points that wear down over time. Even a millimeter of movement can protect a cable from breaking internally. And it's not just sprinkled on randomly, it's applied with specialized dispensers that coat each wire evenly, ensuring no clumps or bare spots. It's almost invisible when applied, but its presence is crucial. This powder layer acts like a silent guardian, reducing friction, absorbing micro vibrations, and even helping during the cooling phase after extrusion. It also plays a role in how the cable handles long-term use. When the cable bends, twists, or stretches, the internal wires can glide subtly inside the sheath instead of locking up. This gliding motion is what extends the life of the cable, especially under daily stress like being coiled, pulled from pockets, or jammed behind desks. The cable remains flexible, Not because the outer sheath is soft, but because the inside isn't fighting against itself. Even during testing, cables with properly applied talcum show fewer failures in the flexibility and stress tests. It's such a small addition, but it's like adding lube to an engine. The system just works better. It's another example of how the tiniest details in manufacturing are often the most important. Most users will never know it's there, but every time a cable survives another bend, another twist, another accidental yank, talcum deserves some of the credit. And then comes the extrusion. Picture a hot pressurized machine forcing molten plastic over the wire core, like squeezing toothpaste onto a brush. The sheath forms instantly, but it's soft at first, so it hits a cooling tank right after, where cold water helps it solidify into that familiar flexible outer layer. Once it's cooled, a quick check ensures the diameter is just right. Too thick, and it becomes clunky. Too thin, and it risks breaking. Consistency here means quality later. At this point, the cable's starting to look familiar, but it's still missing one of the most critical layers: the braid. Now this is the part that's honestly mesmerizing to watch. A USB data cable braiding machine comes to life like a maypole dance, spindles spinning, threads flying as nylon or polyester fibers wrap around the cable with hypnotic speed and precision. It's not just for looks, though yes, the nylon does come in a rainbow of colors and gives cables that textured premium feel. But it's also about strength. This braided layer massively improves wear resistance. Drag it across a desk 1,000 times, stuff it into backpacks, twist it in weird angles. That nylon shell can take it. On some machines, up to 48 carriers spin at once, moving at speeds as high as 360 RPM, creating an intricate woven layer in seconds. And the best part? It's all automated. Just feed in the cable, set the bobbins, and watch the machine perform its dance. What's even cooler is that this braided shell isn't just about toughness. It adds electromagnetic shielding too, especially when woven with tin-plated copper or aluminum magnesium wire. In some cases, the shielding efficiency reaches 60 decibels at 1 gigahertz, which means it's blocking out a ton of interference. That's not something you see, but it's the reason why your cable works reliably in noisy environments. Of course, machines do a lot, but not everything. Human hands still play a role, and a crucial one. There's finesse needed in certain stages that even the most advanced robot arm can't replicate. Not yet, anyway. For example, when it's time to attach the USB connectors, people often prep the cable ends manually. The outer sheath is stripped, the wires exposed and trimmed with precision. Then comes the soldering. USB Type-A, the classic rectangular connector, and USB Type-C. Flux is applied to ensure strong oxidation-free joints, and the heat must be just right. Too hot, and you'll scorch the wire. Too cool, and the solder won't bond correctly. That delicate balance is something no machine can fully feel. It takes human intuition. Some factories have semi-automated soldering stations where machines assist with the repetitive motions, but the prep work and final inspections are still handled by technicians. Technicians often check each unit by giving a firm tug after assembly, verifying the joint's integrity without needing software or sensors. So while machines speed things up and keep the process efficient, the hands-on work adds the reliability. Every cable is checked for visual flaws, uneven sheaths, misaligned connectors, discoloration, or anything that might hint at deeper issues. These aren't just cosmetic checks. A small flaw on the outside can mean a big problem inside, so this final pass ensures that every cable not only works, it looks like it should. Now, here's where things get really serious. Ever wonder how cables claim to survive thousands of bends? There's an actual robot that tests that. It bends the cable again and again in tight angles, simulating the way users twist and turn them in real life. This machine does the same movement over 10,000 times. Eventually, even the strongest cable will snap, but the goal is to find out when. That breaking point tells manufacturers whether their materials and designs are truly holding up to real-world use. The test rig looks simple at first, just a robotic arm moving rhythmically, but it's doing something vital. Each bend happens at a precise angle with measured force, replicating the common abuse a cable takes, being yanked off desks, coiled and uncoiled, twisted while charging in bed, or bent at weird angles inside backpacks. Over time, these small motions can cause internal fractures, even when the outer sheath looks perfectly fine. During this endurance test, high-speed sensors track the resistance and continuity of the cable in real time. The moment even one internal wire breaks or loses connection, the test stops. Engineers then pull that cable apart and inspect where and how it failed. Did the copper strand snap? Did the solder give out? Or did the plastic stretch and shift too much? These failures become lessons, directly influencing future designs. Some cables are tested in batches of hundreds. Results are logged, charted, and compared across materials, manufacturing variations, and even different braiding techniques. It's not just about pass or fail, it's about understanding durability in the harshest conditions. Brands that advertise higher bend counts are often those that invest heavily in this type of stress testing. What's even more interesting is how certain reinforcements, like braided nylon and flexible strain relief designs, consistently extend cable lifespan. In some premium cables, the breaking point doesn't come until after 20,000 or even 30,000 bends, nearly triple the average. Those stats aren't just marketing fluff, they're born from months of physical punishment in testing labs. And it's not just one bend axis being tested. Some setups test side-to-side motion, some test vertical strain, and others rotate the connector while bending the cable, which is a common movement when devices shift during charging. All of this helps build a realistic picture of how a cable survives in hands, pockets, and under desks. At the end of the day, these repetitive motions separate cables that just look good from those that actually perform. That little sticker saying 10,000 bend lifespan? It's backed by relentless testing, mechanical arms, and teams of engineers watching every snap and shift. It's the kind of behind-the-scenes torture that makes sure the cable you grab in a rush doesn't fail when it matters most. Cables that survive longer get rated higher. Some of the best can handle over 30,000 bends. Others start failing around 10,000. Either way, this test separates the strong from the weak and shows whether the braided nylon, the stranded copper, the soldered joints, and the injected casing all do their job as one solid unit. And in the end, it's not just about surviving, it's about delivering. Some cables, like high-performance USB-C models, offer fast charging capabilities up to 66 watts. That's enough to power tablets, laptops, even some small appliances. And to hit that kind of power, everything has to be built to spec. From the wire gauge to the shielding to the soldering and connector type, every part matters. That's the full journey. From the raw copper strands all the way to the final bend test and performance rating, it's a mix of science, engineering, craftsmanship, and high-speed machines working in harmony. And even though a USB cable might seem small, the technology inside is anything but. So the next time one of those cables powers up a phone, syncs your files, or charges a smartwatch, that's not just a wire. It's a result of meticulous design, careful testing, and some truly mesmerizing machines spinning, soldering, and shaping the strongest wire that lives in your pocket. Like this deep dive? Go ahead, hit that. Every single year, over 30 million tons of bamboo are harvested across the world. That's more than the combined weight of all the commercial airplanes ever built. But bamboo isn't just any plant. In fact, it's not even technically a tree, it's a grass. And not just any grass. This is the grass that can take on steel, silk, and even concrete. It's a plant that can grow taller than a giraffe in a matter of weeks, absorb more carbon dioxide than a forest, and regenerate itself without anyone planting a single seed. Bamboo isn't just another green stem waving in the wind. It's a green giant quietly revolutionizing industries, from construction to fashion. And this journey begins in places where acres of these towering stalks stretch as far as the eye can see. These aren't wild, overgrown thickets. Bamboo plantations are carefully managed, functioning more like sustainable farms than forests. Unlike trees that take decades to mature, bamboo grows rapidly and regenerates naturally. When a stalk, known as a culm, is cut, it doesn't need to be replanted. Thanks to its underground rhizome network, new shoots sprout almost immediately, allowing the same plantation to produce for decades without exhausting the soil. Bamboo stands out not just for its growth, but for its environmental benefits. It absorbs 35% more carbon dioxide and produces 35% more oxygen than an equal area of trees, making it a powerful ally in the fight against climate change. It thrives without chemical fertilizers or replanting, making it one of the most renewable resources on Earth. Harvesting bamboo is a precise task. Only mature stalks, aged 3 to 5 years, are selected based on color and texture. Workers use machetes or handsaws to cut them, leaving younger shoots untouched to continue the cycle. These towering stalks, sometimes 60 feet tall and weighing over 100 pounds, are then transported, often by hand-loaded trucks, to processing plants. What happens next is an industrial transformation that turns this green giant into flooring, fabrics, and so much more. The journey of bamboo from stalk to product begins with chopping down the towering green culms into smaller, manageable pieces. These sections are then fed into powerful machines that split the rounded stalks into flat, usable strips, each one cracking open with a loud, unmistakable snap. This is the moment when bamboo stops looking like a wild plant and starts to resemble a raw material ready for engineering. But raw bamboo isn't ready for use just yet. The outer green skin and inner nodes must be stripped away, revealing a pale plank underneath. However, inside that plank are sugars and starches, exactly what mold, fungi, and insects love. To make bamboo last, these must be removed. The planks are soaked in large vats filled with boiling water or hydrogen peroxide, a sterilizing bath that kills bacteria, draws out sugars, and leaves the bamboo clean. Moisture is the next challenge. Raw bamboo holds up to 50% moisture, so it goes into industrial kiln dryers until that level drops to a stable 8 to 10%. Once dried, it's milled into perfect rectangles. These planks can be laid flat for horizontal flooring or turned on their edge for denser vertical flooring. But strand-woven bamboo goes further. The bamboo is shredded into fibers, mixed with eco-resin, and pressed under 3,000 psi. The result? A block of material that can score over 5,000 on the Jonka hardness scale, far tougher than oak. Surprisingly, bamboo also transforms into ultra-soft fabric. Ground into pulp, chemically treated into viscose, and extruded through fine nozzles into acid baths, it becomes silky, breathable thread. That thread is then spun into fabric that's hypoallergenic, antibacterial, and perfect for everything from clothing to bedding. From hard as oak to soft as silk, bamboo truly does it all. Bamboo's dual nature, strong as steel yet soft as silk, has made it a favorite across industries. It's in cutting boards, textiles, scaffolding, and even luxury car interiors. What makes it extraordinary is that it grows faster than any tree, needs no chemicals, and regenerates on its own. From paper and furniture to biomass fuel and construction, bamboo is everywhere. With over 1,000 species suited to different climates and uses, it's cultivated globally, from Asia to Africa and South America. The bamboo industry is now worth over $100 billion and continues to grow. Whether it's scaffolding that bends without breaking or sleek, sustainable flooring, bamboo blends beauty, strength, and environmental responsibility into one incredible, fast-growing solution. Then there's strand-woven flooring, which is so tough that it's used in high-traffic commercial spaces like offices, museums, and even airports. Try dragging furniture across that and see if it leaves a mark. It probably won't. And even if it does, a quick sanding can bring the surface back to life. Bamboo is making quiet moves in the industrial world. Inside premium cars, interior panels made from bamboo composites offer lightweight strength and natural beauty, even helping dampen sound. This blend of sustainability and luxury is becoming the new norm. Beyond that, bamboo fibers appear in surprising places. From toothbrush bristles to structural supports in eco-friendly buildings, it's found in biodegradable straws, sleek furniture, and countless products born from innovation. But bamboo's transformation isn't magic. It's a process. One critical step is drying. Done wrong, it can ruin the material. Done right, it ensures strength and durability. Industrial dryers lower moisture from 50% to around 8 to 10%, stabilizing the bamboo for long-term use. Unlike hardwood trees, which take decades to grow and require replanting, bamboo regenerates from its roots. No soil damage, no clear cutting, no erosion. It simply regrows, making it a champion of sustainability. Properly managed bamboo farms improve soil health, fight climate change by absorbing more carbon dioxide than trees, and support livelihoods without harming ecosystems. It's not just what bamboo becomes, it's how responsibly it gets there that makes it so powerful. On bamboo plantations, local workers often blend traditional harvesting knowledge with modern tools. They carefully select only mature stalks while leaving the young shoots untouched, allowing the cycle to continue uninterrupted. This selective approach keeps the plant regenerating naturally and ensures a long-term sustainable harvest. And there's more innovation on the horizon. Scientists and designers are exploring bamboo's potential in fields like bioplastics, composites, and even medical materials. Experiments are underway to use bamboo fibers in prosthetics, surgical tools, and packaging materials that decompose naturally. No more plastics clogging the oceans. It's no longer just about what bamboo is, it's about what it could become. And the most exciting thing is that this isn't some far-off dream. It's already happening. Of course, none of this works without people, skilled workers across the world, from farmers to technicians to designers, all contributing to the transformation of this humble stalk into a global force. On the plantations, people still walk among rows of towering culms with nothing but machetes, relying on generations of knowledge to choose the right ones to cut. In the factories, workers guide planks into machines that split, shave, boil, and bake them into form. And in the design studios, visionaries imagine what else bamboo can be. Shoes, sunglasses, bicycles, kitchenware, maybe even the next wave of electric vehicle interiors. Every link in the chain matters, and every step reflects how far bamboo has come, from a regional resource to a global game changer. And yet, for all its innovation, bamboo remains humble. It doesn't require fanfare, it just grows. Quietly, efficiently, and incredibly fast. In the right climate, you can actually hear it grow. Some species can shoot up nearly a meter in 24 hours, making them the fastest growing plants on Earth. That kind of growth isn't just impressive, it's game-changing in a world where time and resources are running out. And here's a surprising fact: bamboo is technically a type of grass. Despite its woody appearance and towering height, it's closer to the grass in your lawn than the oak tree in your backyard. But unlike grass, bamboo doesn't stop at a few inches. It keeps going, 30, 40, even 60 feet into the air. And with over 1,000 species, there's a bamboo for just about every purpose, from the tiny ornamental types that decorate living rooms to the giants used for timber and construction. Still, managing this incredible resource takes knowledge. You can't just plant bamboo and walk away. Farmers must know which variety works best for their climate, how to space the culms, when to harvest, and how to care for the rhizome system. With proper care, a single bamboo plantation can provide sustainable harvests for decades. It's the gift that keeps on giving, literally. Now picture this. A factory receives a truckload of 60-foot bamboo stalks. They're green, rough, and full of moisture. By the time they leave the facility, they've been cleaned, stripped, sterilized, dried, pressed, and shaped into products as varied as luxury flooring, soft towels, strong scaffolding, or smooth fabric. It's a full-circle transformation, and it all starts with that first clean cut on the plantation. Now, here's the kicker. The bamboo market is already a giant, and it's only getting bigger. Industry forecasts suggest that the global bamboo economy is heading toward a valuation of over $100 billion. And it's not a bubble, it's a steady climb, powered by real demand, practical innovation, and undeniable sustainability. And while other materials rely heavily on mining, deforestation, or chemical processing, bamboo relies mostly on sunlight, water, and time. That's it. No synthetic inputs, no massive replanting campaigns, just a network of underground roots doing what they do best: regrowing. So what's the catch? There really isn't one as long as plantations are responsibly managed. Overharvesting, monoculture farming, and illegal clearing of natural forests to make room for bamboo crops are real concerns. But with the right balance and oversight, bamboo remains one of the most sustainable resources humans have access to. The story of bamboo is a story of nature's engineering. One plant, fast, strong, beautiful, and versatile, quietly transforming the way we build, dress, furnish, and even heal. And it's just getting started. By now, it's clear that bamboo isn't just a plant, it's a strategy. Nature's blueprint for a better way to build, live, and create. In a time when nearly every industry is rethinking how to cut emissions, reduce waste, and protect the planet, bamboo offers not just an alternative, but a solution that's already proving itself on a massive scale. Every year, over 30 million tons of bamboo are harvested around the world. That's not just a number, it's a reflection of just how deeply bamboo has rooted itself into our modern world. And the growth doesn't stop there. With urban centers expanding, demand for sustainable construction materials rising, and consumer expectations shifting toward eco-conscious products, bamboo is set to play an even bigger role in everyday life. And the beauty of it all? Bamboo doesn't ask much in return. It doesn't demand harsh chemicals. It doesn't ruin the soil. It doesn't even need to be replanted after harvest. It simply grows, renews, and gives back more than it takes. Choosing bamboo over traditional materials sets off a powerful ripple effect. When designers opt for bamboo flooring, they help preserve forests by avoiding the need to cut down trees that took decades to grow. When fashion brands embrace bamboo fabrics, they offer soft, breathable, biodegradable clothing that's gentle on sensitive skin. And when cities use bamboo in construction, they're investing in structures that are both strong and sustainable. Bamboo also brings real-world benefits to communities. It creates jobs in farming, processing, manufacturing, and design, especially in rural areas, while also powering innovation in modern industries. It's not just a fast-growing plant, it's a fast-growing opportunity. But here's what really sets bamboo apart. Hidden inside its fibers is a natural strength-to-weight ratio comparable to steel, flexibility under pressure, and resistance to pests and bacteria. These aren't man-made features, they're natural. Bamboo blends ancient tradition with cutting-edge potential. From scaffolding in Hong Kong to high-end flooring in Europe and eco-luxury fashion in New York, bamboo delivers function, beauty, and sustainability without compromise. It's not just a material, it's a message that we can live smarter, build cleaner, grow without destruction. So the next time bamboo shows up in your life, remember, it's not just good for something, it's good for everything. And now, if you made it this far into the story of the world's most extraordinary grass, there's one last step you can take. Hit that like button if you learned something new. Subscribe to the channel for more deep dives into the incredible materials shaping our future. Don't forget to tap the bell so you never miss the next story like this one.